Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Geometrical, CIS trans or EZ, isomerism arises at each C is equal to C double bond where both carbons of that double bond bear to different substituents. Moving on to the next step. Identify the double bonds in CH2 is equal to CH is equal to CH is equal to CH2, hexa 1, 3, 5, trying. Double bond 1, C1 is equal to C2, positions 1, 2. Double bond 2, C3 is equal to C4, positions 3, 4. Double bond 3, C5 is equal to C6, positions 5, 6. Moving on to the next step. Check each double bond for geometrical isomerism. C1 is equal to C2, C1 bears to H atoms, CH2 is equal to, so both substituents on C1 are identical. No geometrical isomerism possible at this bond. C5 is equal to C6, C6 bears to H atoms, is equal to CH2, so both substituents on C6 are identical. No geometrical isomerism possible at this bond. C3 is equal to C4, C3 is connected to C2, which is part of the vinyl group CH is equal to CH2, and H, C4 is connected to C5, which is part of the vinyl group CH is equal to CH2, and H. Both carbons of this double bond bear to different groups, so geometrical isomerism is possible here. And for the final step, count the geometrical isomers. Only the central double bond, C3 is equal to C4, shows geometrical isomerism, giving two isomers, CIS, Z, and trans, E. Why other options fail? Option B, 3, C, 4, D, 8 would require additional stereocenters or additional double bonds capable of EZ isomerism, but the terminal is equal to CH2 groups eliminate isomerism at bonds 1 and 3. Only one double bond, central, contributes, giving to 1 is equal to 2 isomers. Therefore, the correct answer is A. Therefore, the correct answer is option A.